Hi there. This next wee video is just to show you, it's a wee guide through the next few pages of the Bright Red study guide, where we're finishing off our look at the structure and the bonding of the first 20 elements. So we already talked yesterday about the noble gases, and although they don't have a bonding, we talked about their structure being monatomic. So we're just going to kind of go through each of these first 20 elements and categorize them in terms of bonding and structure. So a nice wee colouring job here. First one there, then we just said that is our monatomic elements. Okay, the next one that we're going to quick think about, there are 7 of them, and they're found mostly over here. These 6 plus aluminium. Now again, I think if you just put your brains in gear, you'll think back to National 5 and think, okay, they are all, what do they have in common? Well, there's aluminium, that's a commonly known metal. All these are metals as well. So what's the type of bonding? The type of bonding is metallic. The structure, metals exist in the solid form as lattices. So these 7 are metallic lattices. Okay, our next wee section that we're going to look at, there are 3 of them here. There's boron, carbon, and silicon as well. They are a form of covalent substance, but there are 2 more as well. Of the remaining white elements that we've not yet coloured in, all of these are covalent. So we're going to take a wee second just to remind ourselves even of what a covalent bond is. When you've got a covalent bond, that's when you've got 2 atoms that are stuck together, and when they stick together, the electron from one and the electron from the other are a shared pair, and that attraction between the shared pair of electrons and the nuclei of each atom is what holds covalently bonded things together. So first of all, our covalent networks. We came across them at National 5, and we've got a picture of our kind of classic idea of a covalent network here. This is showing a tiny wee fragment of a diamond, where every single carbon atom is covalently bonded to 4 other carbon atoms, and the properties are kind of predictable then as a result, because covalent bonds are very strong. So if you were going to be melting a diamond, you wouldn't just be melting wee London dispersion forces like we were talking about previously, but you'd actually be putting in so much heat that you'd be breaking big strong covalent bonds. Okay, so that's the kind of typical idea of what a covalent network is. But be aware though, you get graphite, which is another famous form of carbon. We've got a wee diagram here. It's a bit different. And now that we've covered a wee bit of the higher course, we can actually get our head around a little bit what's going on here. So graphite has got layers of carbon atoms. Each carbon atom in the layer is covalently bonded to 3 other carbon atoms. Now, we would have thought before carbon wants to make 4 bonds, but the remaining electron that's not involved in a bond is actually delocalized. So each of these carbon atoms is contributing an electron that is delocalized across the sheet of carbon atoms. Now, a couple of wee kind of points to draw from that. First of all, you might well remember that carbon in the form of graphite is the only non-metal element that conducts electricity. Well, that is now us accounting for that. That free electron from each carbon is able to carry electrical charge. Secondly, though, okay, we were saying that each of these carbons is covalently bonded to 3 in a sheet of carbon atoms. This diagram here is showing how the sheets are sort of stacked on top of one another. They're held together, and we've got dotted lines between the sheets, which are representing this idea that we came across just the other day, London dispersion forces. That's what's holding the sheets together. Okay, so covalent networks, we've got 3 of them in our first 20 elements. There's carbon, which we know about before, boron as well though, and silicon. They exist as networks. Next chunk that we're going to take a look at are ones again that we're going to be familiar with. So these are covalent networks, so we'll write that in. Next section we're going to take a wee look at are the ones we would have before called them diatomics. So that's our chlorine, fluorine, oxygen, nitrogen, and also hydrogen. These 5 are diatomic elements. But what's the bonding? What's the structure? Okay, the bonding is covalent. The structure this time is molecular. Okay, not a huge deal more to it than that. What we're saying then is that they're held together by covalent bonds, yep, and they're arranged in small clusters of atoms that we call molecules. So covalent and molecular. The last wee thing then, there are 2 elements there, phosphorus and sulfur. Now, all good chemistry teachers have got at home their own model kit, and I've built the structure of what a phosphorus molecule looks like and what a sulfur molecule looks like. They seem like random pieces of information to remember, but you will be expected to be remembering these quite random wee facts. Phosphorus exists as a little molecule of 4 atoms stuck together. Okay, so that's P4. Okay, 4 phosphorus atoms stuck together. Our sulfur, there are 8 of them. So sulfur exists in a ring, and it's sort of like this crown shape. It's got a zigzag type arrangement that you might be able to see if I hold it like that. These 2, again, they're covalent. They're also molecular though. So we'll just get our colouring to complete our wee picture here. Phosphorus and sulfur are also covalent molecular. So that looks like 2 categories that we've got that are the same. But we draw the distinction between them that these ones here that we identified first of all, they are all gases at room temperature, whereas these 2 are solids at room temperature. Now then, our P4 and our S8. If you can think to what we covered recently, which was these London dispersion forces, you might be able to predict which of these 2 substances, P4 or S8, would have a higher boiling point or even a higher melting point, and also why they would. Okay, take a wee second and see if you can recognize, if you can put together some sort of logical reasoning as to which would have the higher melting point and why that would be. If you think about it though, what's going to be happening if you've got a sample of phosphorus that's being melted. It's turning from solid into a liquid. We're talking about lots and lots and lots of these molecules which are held together suddenly becoming free to move. Okay, so what's that going to involve? That's going to involve overcoming London dispersion forces, but the exact same idea is going to be happening here. If you've got a sample of sulfur, what are you doing when you're turning it from a solid to a liquid and melting it? You're putting in enough force so that the various little S8 molecules are able to separate themselves out and become liquids. So this one here, there are 4 phosphorus atoms. Each of them have got 15 electrons, so that will be in total 60 electrons kind of whizzing around those various 4 atoms. Whereas, if you think about each sulfur has got 16 electrons, so I think that works out at 128 electrons spread throughout the S8 molecule. So again, you've got a lot more electrons involved here, which means you could get much more significant temporary dipoles. So the London dispersion forces between the larger sulfur molecules are going to be stronger than the London dispersion forces between the smaller phosphorus molecules. So therefore, you're going to have to put in more heat energy to melt sulfur than you would have to put in to melt phosphorus. So you should all now be able to reproduce this, where we'd be categorizing each of the first 20 elements in terms of their bonding and structure. And you also want to be clear on the structure that sulfur adopts, this crown-shaped ring of 8 sulfurs, and this funny wee cluster of 4 phosphoruses as well, P4 molecule. Okay, all the best progressing on through.